Okay, thank you for joining us today again. We'll continue with SML, which is a functional programming language, one of the first functional programming languages that, in fact, follows closely the notations for functions that we have in mathematics. Basically, you can define a function with the domain and what is the expression that gets computed for every input value. In fact, everything in SML is either a function or a function invocation. Everything is evaluated on the spot, and it basically returns the result of that expression. So you can install SML from the website that you will see in the lecture notes. By default, in Windows, for instance, it will download and install SML, and it will link it from in the path environment variable. So let's overview SML, and then we are going to go into details about how to write programs with functional languages and SML in particular. Good. So functional programming is basically based on lambda calculus. It's the function evaluation is the basic concept of the programming paradigm that is functional programming languages. ML in particular stands for meta language. It was originally introduced in the 1970s as a part of a theorem proving system that was intended for describing and implementing proof strategies for logical computable functions. Theorem prover, logic programming system, whose language PP lambda was a combination of first order calculus, predicate calculus, and polymorphic lambda calculus. That language, LCF, is long gone, but ML was the result of basically that project. ML, or standard ML, is an implementation of ML, and is the basic module. The basic module of SML is the definition and application of functions. There are a lot of other languages that are based on ML, like for instance, you may have heard of OCaml, is an object-oriented functional language. There are a lot of functional languages that are available, including in industry. Scheme is a very popular functional language. Scheme uses another popular implementation of the Lisp dialect by MIT. Also, a lot of imperative languages today have functional features, like for instance in Python, you can return functions as the return of the function. You can return lambda functions. In Java, since Java 8, they introduced lambda functions for event processing programming. Basically, you pass a function, a lambda function, as the parameter of another function. The function that adds an event handler to any graphical user interface component or node in the graph is basically a function. What is the handler? What is the event handler for that specific function? And lately, we have more functional features in Java. You have streams for basically evaluating collections and so on. We are going to talk about some of these functional features, especially in Python, being one of the most popular languages later this semester. So, you install standard ML from sml.nj.org. Once you install it on Windows, you will have to, you type SML in the shell, and that is already added to the path variable. For macOS, the process is a little bit more complicated. You have to add manually the path to the implementation of the SML, which I believe that is in the USR, in root USR local SML directory. I posted a link to that or to that respect on Piazza. So if you go to Piazza, if you don't have SML already installed, although you should have by this time, you can run on Mac SML from this directory. It's USR local SML nj bean, and SML is under that directory. So SML will start the interpreter. This is the interpreter for SML, and it's waiting for us to enter function definitions or function invocations. So to start SML, you type SML or SML-NJ, and to exit SML on Windows, you press Ctrl-Z and Enter. On Mac or Unix, you press Ctrl-D and Enter. Standard ML has as a basic cycle 3 parts. Reading the input from the user, evaluating it, no matter if it is a function definition or a function evaluation, invocation, printing the computing value in the output stream, or an error message if that function is not defined or if there are some exceptions. As a first example in SML, let's assume that we have the empty prompt and we enter the value 3. Every statement in SML ends with semicolon. So 3, it will return that 3 is the integer 3, the value integer 3. The first line contains the SML prompt, followed by an expression typed by the user and ended by semicolon. The second line is basically the SML response with the value that was returned and was the type of that. The reason why we always return it in this format is that when we have functions, it actually returns the domain with the values in the codomain. So you always have this type returned as a response. SML is also a dynamically typed language. It basically infers the type of values out of the operations that are applied to those values. And it basically can infer through type inference the value of the return values based on the values of the input parameters to the function. SML has a number of built-in operators and data types. For instance, it provides standard arithmetical operators like plus. 3 plus 2 will return the value 5. The Boolean values for true and false are available, and the logical operators not and also for conjunction and or else for disjunction. Not of true, since is an inverter, is a negation, it returns false. Not of false will return true. Also, there is a second example with a conjunction, true and also false returns false, because if either one of the two operands is false, then the conjunction is false. Types in SML. As part of the evaluation process, SML does type inference. It basically determines the type not only of the output value, but also of the input value using type inference. There are simple types that are listed here: int, real, bool, and string. And one can also associate identifiers with values. Basically, you can define the identifier 5 and associate it to the value of the expression 3 plus 2. So therefore, whenever you use in the rest of the program 5 represents the value 5. Now, in most programs, you actually don't need variables, because the whole point of functional programming is that you are not using global variables or any kind of loops. You are writing everything as a function definition with arguments that are passed as parameters, and those parameters basically are transformed into the output of the function. So, how do we write functions? Fun, identifier, input parameters within parentheses. Not necessary. You can actually omit the parentheses. In certain cases, you will see later today, equal expression, semicolon. So for instance, the function double takes x as an input and is equal with 2 multiplied with x. Returns that this is a function, double, that takes as an input an integer with values in integer. So how did it actually identify the fact that the input and the output are integers? From the fact that we have multiplication with an integer. So from the type of operations that are used, from the type of other operands that are used in the expression, it identifies that the value of x, which is the input, must be an integer. And now, since 2 multiplied with x is returned as a value, the return value of this function is also an integer. So the double is defined as a function from integers to integers. And basically, it returns the fact that is, like in the mathematical notation, is a function double from integers to integers. Applying a function to any kind of parameters must actually match the formal parameters of the function. So the input arguments or input parameters or actual parameters must be of a compatible type with the formal parameters of the function. So for instance, 2.0 is not an integer. Therefore, we will get an error that we cannot apply the function double on 2.0. The user may also explicitly indicate types. So you can either indicate the input type, like x is an integer, y is an integer, z is an integer, and you can indicate the output type. The return of max returns an integer, and you can basically specify it through colon at the end of the function definition, colon int. If x is greater than 0 and also x is greater than z, using the conjunction and also operator, then x is the maximum of these three. Otherwise, we know x is not the maximum, so all that we need to do is to compare y and z. So if y is greater than z, then we return y, else we return z. Now, when we define this function, the function return will return that this is a max function defined from the Cartesian product of integers with integers with integers. It takes 3 arguments of the type integer, and the output is an integer. So it actually infers the fact that no matter on which execution branch we are returning, x, y, or z must be integers. So the return type of this function is integer. The maximum of 3, 2, and 2 is 3. So basically it returns the maximum of the 2. Okay? The use of recursive definitions is the main characteristics of any functional programming language. And in all of these languages, basically iteration is a no-go. It's basically we always encourage the use of recursion over any iterative constructs, such as while loops. So the truth is that SML contains while loops. It contains loops, but you are not, the whole goal of functional programming is not the fact that we can write iteration, modify the values of variables. Is actually the fact that we can write everything recursively through only definitions of the functions. Either we return basic expressions or we call the function on a smaller instance of itself, recursion. So factorial of x is, if x is equal with 0, it returns 1. Otherwise, we return x multiplied with factorial of x minus 1. So in this example, in the definition in SML, we evaluate the application of the function on the specific arguments, and factorial of 5 returns 120, factorial of 10 returns a different value. Sorry for the interruption. We had a student right now. Let's continue the lecture, and we'll basically cut this from the recording when we post it. Okay, so recursive functions. The use of recursive definitions is a main characteristic of functional programming languages. We saw it in the definition of factorial. And we can invoke factorial on arguments, like factorial of 5 returns a value, factorial of 10 returns a value. If we want to write a function that, for instance, implements the Euclid formula for greatest common divisor, we can implement it as follows. Basically, the greatest common divisor of n and a value that is equal with n, basically the same value, is equal with n. The greatest common divisor of m and n is the greatest common divisor of n and m if m is less than n. And the greatest common divisor of m and n is the greatest common divisor of m minus n and n if m is greater than n. These identities suggest that basically there is a recursive formula for the greatest common divisor. And that recursive formula is the following. If m is equal with n, then we return n. Otherwise, if m is greater than n, then we return the greatest common divisor of m minus n and n, and the greatest common divisor of m and n minus n, the n minus m. So basically, we implement everything recursively, and these are just we do the same in other programming languages. More recursive functions. Let's assume that we want to compute an exponent. We can actually do it recursively. If the exponent is 0, anything to the power 0 is 1. Otherwise, we return b multiplied with the exponent of the base multiplied with the exponent of the base to the power n minus 1. So for instance, if we want 2 to the power 10, we can actually invoke it with 2.0 and 10 and get the response as an exponent. Tuples are a data type in SML, similar to tuples in Python. You have to realize the fact that SML preceded Python with about 20 years or 2 decades. And here we see several examples. Basically, by default, and we will see later when we have lists in SML, we cannot have heterogeneous elements. We cannot have elements that are integers or reals and strings. So the only way to do it in SML, in order to have basically heterogeneous elements, are with tuples. So SML tuples are finite sequences of arbitrary but fixed length sequences where different components need not to be of the same type. For instance, 1 and the string 2 is an element in the Cartesian product of integers with strings. The tuple that is 1, 2, 3 is an element in the Cartesian product of integers, integers, and integers. The tuple that is 4 and the tuple 5.0 and 6 is an element in the Cartesian product of integers with the Cartesian product of reals and integers. You can extract any one of these arguments with the hash function. So the hash of I, where I is any positive number, will extract the element at that index. So for instance, from the tuple 1, the element at index 1 can be extracted with hash of 1 of tuple 1, and that will return the element 1. Similarly, hash of 2 of tuple 2 will return the second element of our tuple 2. If the function hash of I is applied on a tuple that doesn't have enough components to actually extract the element at index I, then an error will of course occur because there is no element to be returned. So let's see what exactly can we do when we don't have the type of the function, so the type of the element. So the identity function is a function that takes an element x and it returns the value of x. So in this case, there is absolutely no way that we can infer what is the type of the element or the input or the output. X could be of any type. The identity function is a polymorphic function. The response that Python will give us, SML will give us, is that this is a function from any type to the same any type. So basically, we can apply the identity function on integers or on strings, and we are getting tuples, in this case, the same integer and the string, and we constructed a tuple. If we want to implement our own function first, second, and so on, like the hash 1, hash 2, and so on, we can implement them in the same way. Basically, first of x and y is equal with x. This is a function applied on any tuple of 2 elements of a type A and a type B, and it returns the type A, an element in the type A as the result. So you see now we have multiple polymorphic, multiple generalized types. Basically, A and B are different types, or could be different types. They could be any types, but only the result has to have the same type with the first argument. That's the requirement. Second is similar. Basically, it's a function from a type A to any type on the Cartesian product of type A and type B with the results in the type B. So the second argument should be in the same type with the result. Switch does the switch of the two arguments. So switch of x and y is y and x. It basically takes elements in the Cartesian product of A with B and returns elements in the Cartesian product of B and A. A means any type. You will see that in certain cases, SML will return two single colon quotes A, which basically means any type that can be compared for equality. The concat function that we will have later basically has this type. So it still means the same thing. It means any type, with the exception that it basically means any type that can be compared with equality. That means that internally in the function definition, we compared an element of the type A with another element of the type A. So it's basically an optimization that when you don't need to compare elements, then you don't need to actually return that the function can be applied only on comparable elements. With elements that need to be compared, SML must remember the fact that this can be compared. We need to compare them. So there will be a warning for this kind of functions that basically are defined on types that must be compared for equality of the following message that we are calling poly-equal for that set of elements. It basically means that two values with polymorphic types for equality are compared. Why does it produce this warning? Because it's less efficient than comparing two values of known types for equality. So basically, it's a warning telling us that it's not fully optimal, the program. How to get rid of that warning? We can change the function to only work for specific types, basically specializing the function. And should you care about such a warning? Probably not, because in most cases having a function that works on any type is more important than having a function that is most efficient possible. So let's actually learn about other data structures in SML, and the most important one is lists. A list in SML is a finite sequence of objects, all of the same type. So for instance, we can create a list of integers, a list of Boolean values, or a list of other lists of integers, but all of the elements must be of the same type. So you can see here that the first element is a list of integers, which means that the second and the third elements must also be list of integers. So for every one of these values, Python SML will return, in fact, what is the type of the value returned. So this is a list of integers, this is a list of booleans, this is a list of integers. You always read such types from the right hand side. That is the most general case. It's basically what is the collection and then what's the type of the elements of that collection. So the last example is a list of integers. All the elements have to be of the same type. So for instance, a list like this one, the list that contains 1 and the list that contains 2, is not actually well defined in SML. The operand and the operator do not agree. The operator being the list does not have elements of the same type, because the type of the first element was int, the type of the second element was list of int. Empty list is basically a list that is of any type. So again, we have this polymorphic type that a list of any type is the empty list. The moment that you are adding elements in the list, we will see later with the cons operator, we basically get a list of a specific type. The type is described in the terms of, again, the variable a, which stands for any type. But the moment that we are inserting any element in that list to create a new list, now we have a parameterized type. So the empty type itself is unparameterized, but once we add elements, it becomes parameterized. So what are the operations on list that we can do? In effect, there are three functions: head of the list, the tail of the list, and we will see later the cons operator that will take an element and the list and creates a new list that contains that element as the head, and the rest of the list is the tail of the list. So the function head returns the first element of its argument list. So for instance, the head of 1, 2, 3, the list 1, 2, 3 returns 1. The head of the list that contains the list 1, 2 and the list 3 returns the first element, which is the list 1, 2. So applying this function to an empty list will result in an error because there is no head of the empty list. The tail of the list removes the first element and returns the rest of the list. a list of the remaining elements. So the tail of 1, 2, 3 returns a list that is 2, 3. The tail of the list that contains the list 1, 2 and the list 3 returns the list that contains the list 3. The application of this function to the empty list will again produce an error because there is no first element to be removed to get the tail of the list. This can be constructed also with the binary function cons, which is basically double colon. It adds the first argument. This is an infix operator. It acts or function. It adds the first argument to the front of the second list, the second argument. So, for instance, 5 cons the empty list is the list that contains 5. 1 cons the list 2, 3 is the list that contains 1, 2, and 3. 1, 2 as a list cons the list that contains the list 3 and the list 4, 5, 6, 7 returns the list that contains the list 1, 2, the list 3, and the list 4, 5, 6, 7. So the arguments again have to be of the same type. The left-hand side of the cons operator should be one element, so the type should be of one element in the list that is the right-hand side. So for instance, in this example, it doesn't work because the list that contains 1 is a list of integers, and the type of the elements that we have in the list 2, 3 are integers. So list of integers with integers are not compatible, therefore the operand and the operator do not agree, and we get an error in this case. So cons only works with one element and a list of elements of the same type. Lists can also be compared for equality, and like in Python, the order of the elements in lists matters. So the elements have to be in the same sequence as in both lists. So the list 1, 2, 3 is equal with the list 1, 2, 3. However, the list 1, 2 is not equal with the list 2, 1, so we actually get the result of comparison, we get false. The tail of the list that is 1 is the empty list, which is equal with the empty list. So even if we know that after eliminating 1, we get an empty list which is actually of integers because we eliminated 1 out of it. So the result is a list of integers that is equal with the empty list of non-parameterized type. So basically parameterized is the type, but it's still the empty list. So how do we define any kind of functions? Like if we want to extract an element of a list, or we want to concatenate two lists and so on, we have to write it through recursion. Basically, we have to consider at every point that if we take a function, we'll have to, which uses lists, we have to actually think about how to write the most, basically, recursive, the base cases, the base case, and the recursive definition or relations for that list. So in defining list functions, it's very helpful to keep in mind that a list can be either empty or the result of cons of x and y. That means that the list contains at least one element, and we can get that element with the head function and the tail of the list. So if we want to write a concatenation method, a concatenation method that takes two lists as inputs, the easiest way to define it is to write a recursive definition. Basically, when are two lists concatenated, the base case? When one of the lists is empty. Usually the first list is empty, and then the second list concatenated with the empty list is the same list. So we can basically write the base case as an empty list concatenated with any list is that list, and then the recursive case that a list that contains a head concatenated with another list, we extract the head and we call recursively concatenate the rest or the tail of the first list and the second list. So in designing in such a function, we basically consider the inputs to be x and y as two lists, and there are two possible cases which are exclusive one to each other. If x is an empty list, then concatenating x with y yields y. Basically, empty list concatenated with anything is that anything. If x is of the form x1 and x2, then x1 as the head and x2 as the tail, then concatenating x with y will basically result in a list of the form x1, the same head with x, and z as the tail, where z is the result of concatenating the tail of the first list, which is x2, with y. So we can actually think more specifically in terms of the head of the list and the tail of the list. So we basically extract the head of the list, and now we are calling concatenation on the tail of the list, which is a smaller instance of the problem. Eventually it will reach the empty list, and on the way back it will add each one of the heads that we took out back into the concatenation. So we are actually getting the concatenation of both lists. And this is only done through functions. So we do function calls for every single invocation. So we apply functions to function results. It's like combinations of functions. So now we can see the result. So the concatenation of x and y is the following. If x is the empty list, then empty list concatenating to y is y. Else, we apply the cons function on the head of the first list. So we extract the first element, and the result of the concatenation function, we call recursively, on the tail of x and y. All of these are functions. So basically we apply concat on the result that we get from tail of x, which returns the rest of x, and y. Let's consider that this executes, because through recursion we are actually getting back the result. Then we apply the cons function on the result of the head function with the result of that concat. So we basically, it's a combination of functions. We combine the concat function or cons function with the result of head function and concat applied to the tail function. So we first evaluate the inside expressions like tail and head, and then we evaluate concat, and then we evaluate on the final results of concat and head, we apply cons. So let's see how, for instance, cons or concat of 1, 2, and 3, 4, 5 works. It basically calls recursively cons of the head of 1, 2, so which is just 1, with concat of the tail of the first list, which is 2. It calls concat of the list that contains 2 and the list that contains 3, 4, 5. Which in its turn, it will compare. Is the list that is 2 equal with empty list? No. So it goes on the else branch and calls cons of the head of 2, which is just 2, with the result of concat of the empty list and 3, 4, 5. And that will return through the base case the list 3, 4, 5. And now we can apply cons between 2 and 3, 4, 5, which gives us 2, 3, 4, 5. And then on the way back, in the first function, invoked function, we apply cons of 1 and 2, 3, 4, 5, and we get the final result, which is 1, 2, 3, 4, 5. So in fact, everything that we did was function composition. We apply functions on the result of other functions that are evaluated first. And this happens all the time for all of this. So it executes on a stack, like it executes on any other programming language. There are no variables, because all that you do is either if statements and applications of functions. So you shouldn't use any variables. There are those aliases that you saw with val defined at the beginning of the class, but you shouldn't use them, because by default, you basically get these results. So I see that there are a few questions in the chat. Fizam asked if you can add elements to the end of the list. No, you cannot, unless you write a function to add elements at the end of the list. So I will show it to you here in the interpreter itself. So the question is, can we define a function? Let's call it add last, which adds elements to the end of a list. So we want to add x in a list L at the end. So what's the base case? The base case is when the list is empty. If the list is empty, then we return the list that contains X. Basically, we put X at the end of the list. Else it basically means that we take the head of the list L and we const it with add last of the element X in the tail of the list L. So we apply the tail function, then we apply the add last function, and then we apply the head function, and we apply the const function to get the final result. So for instance, let's say that we want to add at the last element of a list, we want to add 5 at the end of the list 1, 2, 3, 4. And now I have basically 1, 2, 3, 4, 5. I'm adding to the end of the list that element. So this is basically the definition. I always have to think in recursive terms. I have to find the base case, and then I have to apply the function recursively. I have to find the recursive case. Okay, excellent question, by the way. Okay, length. So this function computes the length of the list. So the length of an empty list, the length of the list nil is 0. The length of any other list is the length of the tail of the list plus 1. So it calls recursively the length of the tail of the list, and then it adds 1 to it. So the length of the list 1, 2, 3 is 3. The length of the list that contains the lists 5, 4, 3, and the list 2, 1 is 4. It basically finds how many elements are at the first level in that inner list. And the length of the empty list matches the base case, so it returns 0 immediately. Doubleall. So this is a function that takes a list, and for every element it doubles that element and returns it into a new list of doubles. So in this case, I multiply the head of the list with 2, and I call recursively doubleall on the tail of the list, and finally I const, basically I create a new list that contains as the first element the double of the head, and as the rest of the elements the result of doubleall on the tail. So always you have to write things recursively. You have to basically write what's the base case, and what happens in the recursive case, what it would be the value of, let's say, the first element, and the rest of the list will be computed recursively with a call to doubleall. What about reversing the list? Now, a naive solution would be to just reverse the tail and then concatenate it with the head of the list. So there is a problem with this, even if we are using this symbol, which in fact is just the built-in operator in SML for concat. The cost of this function is n squared. And the reason for that is that concatenation takes in the length of the first list. So if we would have to write the time that is taken by every one of these functions, let's actually write it in an editor. Oops. So the time to reverse a list of n elements is basically equal with the time to reverse n minus 1 elements, so t of n minus 1, plus the time that it takes to do the concatenation. But the concatenation of a list of n minus 1 elements to one element is basically you take the head first element and you call recursively the concatenation on the rest of the first list, and so on. So the cost of that is n. So t of n is equal with t of n minus 1 plus n. And if you apply this formula, basically t of n minus 1 will be t of n minus 2 plus the size of n minus 1 plus the size of n. And if you continuously apply this in the end, after many steps, you basically get 1 plus 2 plus and so on up to n, which is basically in the size of n squared. So we write this notation O(n) squared, which most of you already saw in several courses that you took with us. So this is very inefficient. It's at least for reversing a list. Reversing a list in any other programming language would not take you this cost, quadratic time. So you need to find a better. We need to find a better algorithm for reversing lists, and we can do it in one way, with basically using an accumulator. So an accumulator will give us better time. So reverse helper is a function that takes a list L and another list L2, and if L is nil, it returns L2, otherwise it calls reverse helper with the tail of L and the result of cons of the head and L2. And then reverse of the list L is reverse helper of L and empty. So what exactly happens? Let's assume that we are calling reverse on list 1, 2, 3. Let's actually write it down. So we call reverse of 1, 2, 3. In fact, in SML, if you have a single argument, you can actually omit the parentheses. You can just write reverse 1, 2, 3 as a list. So this will call reverse helper of 1, 2, 3 and empty. Okay. Let's just use reverse H for helper. So it fits into one line. Now, what does this call? So we can see if the list is empty, is not, call reverse helper on the tail and the head of the list L cons the list 2. So this will call reverse helper of the tail, which is 2, 3, and 1 cons the empty list. But 1 cons the empty list is the list that contains 1. Now we apply the function definition again. So this calls reverse, because what 2, 3 is different than empty, calls reverse helper of the list that contains 3 and the result of the cons of 2 and the list 1. But that is basically in step of 1 to 1, which calls reverse helper. Again, the list 3 is different than empty, calls reverse helper of the empty list and the list 3 to 1, basically 3 cons 2 and 1, which now, because of the fact that empty is equal with empty, returns the second parameter, which is 3 to 1. So instead of doing that append, at each step we are actually paying only the cost of one operation, which is put the element from the head of the first list into the head of the second list. So if we compute now the time of this function for any length of the list n, that would be t of n minus 1 plus 1. And if you apply this, basically this is equal with t of n minus 2 and one step for computing the value and another step for the previous value 1. And this will give us exactly n steps. Basically, when we reach 1, we have the 0, we have the base case, and then we have 1 plus 1 plus 1 plus 1 n times. So this is in the size of n, which is linear time, much better for reversing a list than actually quadratic time as we had before. So let's continue with other functions. How to write a function to remove all the occurrences of the first argument from the second argument. So remove of an element x from a list L. If the list is empty, we return empty. If the list x is the head of the list L, then we remove the element x from the tail of the list L. Otherwise, we return the result of cons of the head of the list L and the result of remove of X and the tail of the list L. So basically, if X is the head of the list, then we call recursively remove X from the rest of the list. We don't keep the head of the list. Otherwise, we keep the head of the list. So we keep only those elements that are different than X. And we have the base case that when we reach the empty list, there is nothing else to remove. We return the empty list. So for instance, removing 1, removing all the occurrences of 1 from 531, we return the list 53. Removing 2 from the list 4242422, we'll actually return the list 444. We remove all the occurrences of 2 from that second argument of the function. So now if we want to write a function that we basically remove all the duplicated occurrences of elements, we can use the previous function. So in fact, all that you need to remember in functional programming is that is applying functions to the results of other functions. It's basically combining the definitions of functions in such a way that we implement the requirements. So it's very useful because basically you can always write functions in the most simplest and basic way. That's why functional programming is so powerful and so popular today. It's used in a lot of applications, including distributed computing. You may have heard of MapReduce. MapReduce is actually application of the functions map and reduce and distributing the data over multiple computers, and then basically applying the functions to combine the results in order to get a final result from all of the queries, from the queries on all of those computers. So let's assume that we want to implement a function remove duplicate that removes all the duplicates of the elements of a list. So first, if the list is empty, we return empty. There are no duplicates to be removed anymore. Else, we keep the head of the list, so we keep the first occurrence of the element, and then we call the recursively remove duplicates of the result of remove all the occurrences of the head of the list from the tail of the list. So what this does, it removes first the element that we kept in the result from the rest of the list, and then calls recursively remove the rest of the duplicates. So even if there were elements equal with the head right after the element head, we actually got rid of all of them. So this function removes all the duplicates. It returns a list of only the first occurrence of every element of the list. So remove duplicates from this list. The moment it keeps 3, but it removes all of the other 3s in the list. And then it keeps 2 and removes all of the other elements. So this 4 is removed and so on. Any questions? Okay, great. Okay, now there are multiple ways to define functions in SML. The way that we define functions with if statements is very useful for functions that basically have complicated conditions. But in SML, because it's a pattern matching language, basically we can represent functions not only through if statements and using mathematical logical conditions in the if statements, but we can also generate patterns. Basically, the pattern of the input, for instance, if the input is an empty list, we would immediately notify and basically return the expression corresponding to that pattern, to that empty list. So a function can also be defined with patterns, which the standard syntax is that the function identifier on that pattern is equal with an expression computing from that pattern. Else, we have again the identifier, the name of the function, followed by a different pattern, maybe lists that contain one element, like x cons some tail y. And then we return another value, expression 2, and so on. So the identifiers should be all the same, the name of the functions. All the patterns are of the same type, because through type inference, the type of the inputs and the type of the outputs is inferred. And all the expressions are of the same type. The results must be of the same return type. The patterns will be expected in order, and the first one that matches the value returns the value of the function. So for instance, our reverse function that we had in the previous example can be written with patterns. This is the inefficient version of reverse. Basically, it says that reversing an empty list is an empty list. Otherwise, reversing a list that takes that has at least one head x and the tail xs is equal with reversing the tail xs append, which is the @ sign, the list x. So basically, we define it through two patterns. We defined one case and then another one that is completely different. It's exclusive to the first case. The first case says lists that do not contain elements, and the second one says lists that contain at least one element. So the definition by patterns is just optional. It's a different notation syntax that is used in SML. In some cases, may be a little bit easier. I have about 20 examples that follow, in which I'm basically defining set functions, both with if statements or basically functions if, and with patterns. And those are all about set operations in SML. So let's assume that we have lists that represent sets. How do we write a member function? A function that takes an element and a list and checks if the element is a member of the list. We all write them with patterns, with recursion. If the list is empty, then we return false. We don't need any return statements, remember, in SML, because everything is function definition. In the then clause, you can only have an expression that gets returned, and same in the if clause. You can't have any kind of sequential code or statements like you have in imperative languages. That's the difference between functional languages and imperative languages. Else, if the head of the list is equal with x, then yes, x is a member of the list, we return true. Else, we call recursively, is x a member of the tail of the list? The same function can be defined with patterns. The function member applied to the x and the empty list is equal with false. X cannot be an element of the empty list. Or x is a member of a list that has a head y and a tail ys. If x is equal with y, then we return true. That means that x is equal with the head of the list. Else, we call recursively member of x and the tail of the list ys. So the two definitions are very close to each other, only that one is all done through if statements, the other one is done through patterns. So basically, we write only specific definitions. We say that member of an element in the empty list is false. Member of an element of a list that contains at least one element returns this value, which is an if statement itself. By the way, I don't know if I mentioned earlier, if you want to put comments in SML, you can enclose them within open parentheses star and then your comments and star close parentheses. It's very useful to have comments in text in code, so this is extremely useful. So let's see more definitions both with if statements and patterns related to lists. So how do we implement a union of two lists? The union of two lists that represent sets is similar to concatenation, but basically we eliminate duplicates. So if the first list is empty, then the second list is the result of the union. Else, if the head of the first list is a member in the second list, then we call recursively the union of the tail of the first list and the second list. So we don't keep the head because it's already a member of the second list. Else, the head of the first list is cons with the result of the union of the tail of the first list and the second list. So basically this member just checks that the element of the first list is an element in the second list. If it is, we don't keep it in the duplicated in the union. If it's not, we keep it in the union. So for instance, the union of these two sets will eliminate the 5 in the first set, so we basically get all the elements uniquely. The union of the empty list with 1, 2 is the list 1, 2, and the union of 1, 2 with the empty list is the list 1, 2. And this is all computed through recursion. Now, if I have to write it with patterns, I would do it very similarly. Basically, the if statement that I had in the first case is one pattern. The union of the empty list with any list is that list. And then I have the second pattern, that the union of a list that contains the head x and the tail access with the list L2 is equal with, if X is a member of the second list, then we just compute the union of the tail access and the second list. Else we keep the head, because otherwise we don't have it in the union. So patterns are very, very similar to if statements. Intersection. Intersection is the set of elements that are in both sets L1 and L2. So for instance, if one of them is empty, like L1 is empty, then there is no element in the intersection, because the intersection contains elements that are in both. If the head of L1 is a member of L2, then we return the head of L1 cons the result of the intersection tail of L1 and L2. So head of L1 is already in L1, is the head of L1. If it's also a member of L2, and we implemented member 3 pages ago, basically in the lecture notes, then the resulting intersection must contain the head. Otherwise, we call recursively the intersection on the rest, the tail of the list L1 and L2. So we keep elements only if they are in both sets, L1 and L2. So for instance, the intersection of these two sets is only the list of the element 5. 5 is the only element that is in common in the two sets. If we have to write it with patterns, very easily, the intersection of the empty list with L2 is empty. The intersection of L1 with empty is empty. The intersection of a list that contains a head X and the tail XS with a list L2 is the following. If X is a member of L2, then we return X. Basically, X is in both the first list and the second list. So we return X cons the result of the intersection of the tail XS and L2. Else, we return the intersection of the tail XS and L2. So the intersection of these two lists is just exactly the element 5. So writing it with patterns or with if statements is basically the same. Subset. We want to check if L1 is a subset of L2. First of all, the empty list is a subset of any other list. The definition of subset in set theory is that are all the elements in L1 in L2? This is vacuously true if L1 is empty. All the elements are in the other one because there are no elements in L1. So if L2 is empty and we already are on the else branch that there were elements in L1, then we return false because there are no elements to actually anymore check. Otherwise, if the head of L1 is a member of L2, we call recursively a subset of tail of L1. We check if the rest of elements of L1 are in L2. Otherwise, it means that at least one element is not in L2 from L1, and therefore L1 is not a subset of L2. So here we have two examples. The set 1, 5, 7, 9 is not a subset of 2, 3, 5, 10 because 1 is not an element of the second list. However, the set 5 is an element of 2, 3, 5. We can also define subset with patterns. Again, basically the same way that we define intersection and union is done with patterns in this example. I will skip it because we already did it. We actually can simplify this much easily because the first pattern already fired, so the second pattern is not really necessary anymore to write with an if statement. Basically what it says is that if L1 is a subset of empty, by default must be no, because if the first one fired, it should have been already true. Okay. Set equal. Set equal can be implemented with subset. Is it true that L1 is a subset of L2 and L2 is a subset of L1? That's exactly the definition of set equal. All the elements in L1 are also in L2, and all the elements in L2 are also in L1. And you can see here the set 1, 5, 7 is not equal with 7, 5, 1, 2, but the set 1, 5, 7 is equal with the set 7, 5, 1. Why? Because every single element in the first list is in the second list, and every element in the second list is in the first list. We can also implement minus of two sets. Basically, it's the set of all the elements that are in the first set but not in the second set. The base case is minus of the empty set minus the any set is the empty set. There are no elements in the first set that are not in the second one. Second definition for pattern only. If we have a list that contains the head X and the tail XS, if X is a member of L2, we don't keep it in the result of the set difference. Otherwise, we keep it in the result of set difference. And we call recursively minus or set difference on the tail XS and the second list L2. Cartesian product is a little bit more complicated. So what is Cartesian product? Basically, we should write it as an example here. So the Cartesian product of two sets, like for instance 1, 2 and 3, 4, would be equal with the set of all the tuples where we have one element in the first set and one element in the second set. So it would be 1, 3 and 1, 4, followed by 2, 3 and 2, 4. Okay? So we take one by one every element of the first set and we group it with every element in the second set. So we basically get 1, 2 and 1, 3 and 1, 4. So the result of Cartesian product is really the result of product of 1. Take one element and the list and construct all the possible tuples. And then union of that with the result of product of the tail of the list, of the first list and the second list. So we will start with, in SML, because it's a functional programming language, every helper function must be defined before we are defining the higher level function. So product 1 is actually the first one defined by the product function for Cartesian product is really the second one defined that is using product 1. So always you have to define them in that order. Or even if you are developing a top-down product, you basically implement the requirements, you have to basically write first the helper functions first, because you can't define a function that uses the result of another function that was not yet defined. So first is product 1. Product 1 takes one element and the list and constructs all the pairs of that element with elements of the list. If the list is empty, then it returns empty. There are no pairs possible to be created. X product 1 with a list that contains the head Y and the tail YS is a tuple XY cons the result of product 1 of X and YS. So basically we call recursively product 1 on the rest of the list, but we add on the way back the tuple XY, X and the head of the second list to the result. So for instance, product 1 of 1 and 2, 3 is really grouping 1 with 2 and 1 with 3. So it will be basically a list of tuples. Now, product of the empty list and the list 2 is the empty list. We can't create tuples if the first list is empty. Otherwise, we basically have a list that has at least one element, which is the head of the list X and the tail XS. We call product 1 on X and the second list, which creates all the tuples with the first element and the elements of the second list. We call product of the rest of the elements XS in the first list, the tail and L2, and then we union the two sets. So basically when we create any product of two sets, we first group the head with any one of the elements in the second set. So we have, in this example, 1, 2, 1, 3, 1, 5, and 1, 10. And then we call recursively product on the rest of the first list and the second list. So basically it creates tuples from 5 with 2, 3, 5, 10, and so on. Other operations that we have to do with sets is power set. Now, power set is a little bit more complicated. In fact, I will explain it to you first through an example. So let's take a set. Like for instance, I want to compute the power set of the set that is 1, 2, 3. Okay? The question here, because everything has to be solved through recursion, is really what is the connection, what is the basically how can we obtain the power set of 1, 2, 3 if we compute recursively the power set of 2 and 3. So let's actually see what is the connection between the power set of 2 and 3 and the power set of 1, 2, 3. So we can consider that maybe the algorithm already gives us the power set of 2 and 3. So what is the power set of 2 and 3? Is the set of all the subsets of 2 and 3. So it's the empty set, the set that contains 2, the set that contains 3, and the set that contains 2 and 3. Okay. One thing that we can see with the power set of 1, 2, 3 is that the power set of 1, 2, 3 already contains all of these elements. So it's empty set, the set that contains 2, the set that contains 3, the set that contains 2 and 3. But it contains also other sets. So for instance, the set that contains 1, the set that contains 1 and 2, the set that contains 1 and 3, and the set that contains 1, 2, and 3. And those are all the elements of the power set of 1, 2, 3. So in fact, we can compute a power set of 1, 2, 3 recursively. So the power set of 1, 2, 3 is really the power set of 2 and 3 and union, let's just use U for union, union of inserting 1, the head of the power set, into each one of the results of the power set of 2 and 3. Because we obtained the 1 by inserting 1 into it. So we have the empty set, now we have 1. We have 2, we have now 1, 2. We had 3, we now have 1, 3. We had 2, 3, now we have 1, 2, 3. And this is the power set of 1, 2, 3, because we have empty set, the set contains 1, the set contains 2, the set contains 3, the set contains 1, 2, 1, 3, 1, 2, 3, and 1, 2, 3. So we can basically implement first a method insert in all the sets that we get as result of the power set of 2 and 3, 1. We can union that with the set 1, 2, 3, and we obtain the set, the power set of 1, 2, 3. So basically, we call recursively to obtain the set of 2, 3, and then this power set of 1, 2, 3, the order doesn't matter in a set, is the union of that power set and the set obtained by inserting 1 in each one of the power of the set's elements of the power set of 2, 3. And that actually gives us the power set of 1, 2, 3. Okay? So now that's exactly how do we implement it. First, we need a function to insert in every one of the subsets of a list. Like for instance, if we insert in the list that contains the list empty and the list 2 and the list 3 and the list 2, 3, 1, we get basically 1, the list 1, the list 1, 2, the list 1, 3, and the list 1, 2, 3. So insert all takes one element and the list of lists of the type of that element. If the list is empty, then there is nothing, it cannot be inserted in any one of those elements. So we return empty, that's the base case. Otherwise, we create a new list, which is E inserted in the head of the list L. So E1 inserted in the empty list. And then we call recursively insert all of that element E in the tail of L. So basically we compute the rest of the insertions of 1 into the other elements, into the other elements, yes, of the original list. So now we can implement power set. So power set of any list L is first of all the list of the empty list. The power set of the empty list is the set of all the sets that are basically subsets of the original list. And empty list is a subset of the empty list by default, recursive true. So the power set of the empty list is really the set that contains the empty list. After that, we have the recursive definition. The power set of a list L is the union, or basically append, of the power set of the tail of the list L, and the result of inserting in all of the results of the power set of the tail of the list L, the head of the list L. And you can test it. These are examples that you can run in the command line, and you will basically see that this is exactly what SML returns for all of those examples. So all of the examples that you will find in the lecture notes are basically executable. You can cut them and paste them in the SML interpreter, and they will run fine because they are all implemented correctly and tested by me. Excellent. Okay. SML also has other types. For instance, has a type for records, which could be used to store kind of like dictionaries where you have a name associated with a corresponding value. And in fact, if you try to check if two records of basically the same dynamic data fields or data fields and values are the same, it will respond that is true. Like a Toyota Corolla 2017 is the same with make Toyota model Corolla 2017 with the same color. Okay. You can also define your own user types, which is close to object-oriented programming. But again, these are not important in the case of a functional language. In the case of a functional language, all that you are required to basically learn as the main focus is the recursion and the basic data type of lists. Everything else can be built on top of that. So, unfortunately, we don't have more time today, and we are starting actually a very hard, heavy part in our lecture for today. Higher order functions are difficult to understand, so we are going to cover them in the next lecture. Thank you very much for today. I will also record and post this recording on SB Connect, and I hope that later we will be able to post them as videos somewhere. So thank you, and see you on Monday. Thank you very much. I will stop the recording and post the recording on